We are now yet to see what we call calculations on or calculations involving electrolytic conductance or electrolytic conductivity. Those are the calculations that we want to see. I'll begin with the first question. The first question says, part A, state what is meant by the cell constant. I know you can define this. Then part B says the resistivity of a 0.02 molar potassium chloride solution is 361 ohm centimeter, and the conductivity cell having such a solution was found to have a resistance of 550 ohms. Roman 1, calculate the cell constant. Roman 2, if the same cell was filled with 0.1 molar zinc sulfate solution, and had a resistance of 72 ohms, then calculate the conductivity of a 0.1 molar zinc sulfate solution. That's the question we have. Interpret the question very well. What's meant by the cell constant? You can define that. Resistivity of a 0.02 molar potassium chloride solution. Resistivity. We are given resistivity as 361 ohm centimeter. We are given the resistance as what is this question? We are given a resistance as 550 ohms. That is our resistance. So if that is our resistance given to us, the question is asking us to get the cell constant. calculate the cell constant. All of you are aware that cell constant is L over A. L is length, A is cross-sectional area. But in the information given, there is nothing like L, there is nothing like cross-sectional area. What shall we do? What shall we do? Get the formula of resistance or resistivity and find a way of putting in the cell constant the way we did in our previous calculations. So what shall we do? We shall say from resistance is always given as, do you remember that formula that has L over A in it? Resistance is equal to resistivity L over A. Hope you remember that formula. Resistance is resistivity multiplied by L over A. That's the only way we can bring in the cell constant. So if we want the cell constant, we shall say resistance is equal to resistivity times the cell constant. This implies that the cell constant is resistance over resistivity. So cell constant is equal to the resistance 361 ohm centimeter over resistance 550 ohm. Is that right? Cell constant is resistance over resistivity. Yeah, this is resistance over resistivity. So we are not substituting in well. We have cell constant as resistance. Our resistance is 550 ohms over resistivity 361 ohm centimeter. Ohm cancels out. Your answer comes out as, when you divide this, you get 1.5235 per centimeter. Centimeter is at the bottom, so then it becomes a centimeter. That is the cell constant. And you get your marks from that. Then, part 2 tells us that what happened if the same cell was filled with, now the potassium chloride was removed and they put there zinc sulfate solution. The resistance changed because different solutions have different resistances. So for zinc sulfate, resistance is now 72 ohms. But I told you the cell constant is always a constant, whichever, so long as the cell is the same. So only the electrolyte that is changed, cell constant remains the same. So cell constant that we have got there is what we shall use here. It's 1.5235 per centimeter. They're now asking us to get the conductivity. They're asking us to get the conductivity. If they say conductivity and then they don't specify whether more electrolytic, that means they are meaning electrolytic conductivity. Electrolytic conductivity, we saw its expression as the reciprocal of resistivity. But which resistivity is the same as, resistivity is the same as Ra over L. That is the resistivity. So this implies that kappa is the same as 1 times L over Ra, which is the same as 1 over R times L over A, which L over A is now the cell constant. We have the R as 72. We have the cell constant as 1.5235. So when you do a good substitution, you get your kappa as 0.02116. What are the units? Per ohm. Okay, let me write this on the next page. Oh, I think I can write it here. Kappa 0.02116 per ohm, because the ohm is the denominator here, then per centimeter. Should I assume everything is fine as per that calculation? So they wanted you to get the cell constant and then use the cell constant and play around with the formula for kappa, substitute, get your final answer. Are we together?
Yes, teacher.
Okay. Now, that is our example 1. Let's look at the second example. The second example is this one. Example 2. It says, state what is meant by the term. No, that's example 1 that I'm repeating. It says a conductivity cell. Conductivity cell with electrodes two centimeters squared in area and 1 centimeter apart has a resistance of 7.25 ohms when filled with a 5%. Oh, this is interesting. With a 5% potassium chloride solution. Calculate the Roman 1 cell constant, Roman 2 conductivity, of the potassium chloride solution. Part B, if the same cell was filled with 0.02 molar potassium chloride with a resistivity of 361 ohm centimeter. Calculate the resistance. There we go. What do we have? We have the cross-sectional area as 2 centimeters squared for each electrode. We have the L, which we call the distance, as 1 centimeter. We have the resistance as 7.25 ohm. Will this be useful? 5% potassium chloride? I don't know, but you know what it means? What does 5% mean? 5% potassium chloride solution. It means that 5 grams of potassium chloride, which is a solid, are dissolved in every 100 centimeters cubed of water. That's what it means. Dissolved in every 100 centimeters cubed of water. And that implies that you can calculate the concentration. If you have that information, you can get the concentration of that solution. But will it be important at this point? Let's see later. The question is asking us to get cell constant. Here, cell constant will not waste a lot of our time. Cell constant is simply L over A, which is 1 over 2, which is 0.5 per centimeter, because we have A and L. So we can get it directly from there. So here cell constant will not disturb us. We shall just get it as L over A and get Roman 1 done. That is our answer for Roman 1. What next do we need? We need to get the conductivity of the potassium chloride solution. They talk of conductivity here, they are talking of kappa. They're not talking of molar conductivity, because it's not, if they want molar conductivity, then they will specify. But we do. We want to get the electrolytic conductivity. That's Roman 2. Electric conductivity is 1 over R. I want you now to understand this formula, because we have used it several times. Why am I writing that formula? Because I've already got L over A here, which is the cell constant. So it will not waste a lot of my time to deal with it. So I have L over A, I have R. So what is R in this question? R is the resistance, 7.25 ohms. The cell constant is 0.5 per centimeter, according to this. So what is my final answer? When I do this calculation here, my final answer would be 0.06897 per ohm. If you don't remember the units, they can be derived here per ohm. Then the centimeter is already up per centimeter. That's the electrolytic conductivity. Maria, are you following?
Yes, teacher.
So that's it. Now, after getting that, we can deal with our part B. If the same cell was filled with a 0.02 molar potassium chloride solution with the resistivity of that, calculate the resistance. So when they tell you the same cell was used, that means the cell constant remains the way it is, because it is the same cell. It is L over A, 0.5 per centimeter. They're telling us that the resistivity now became 361 ohm centimeter. And what are they asking us to calculate? They want us to get the resistance R. You know the formula for resistance. Resistance is both as resistivity times L over A, which is 361 times the cell constant. Okay, so that gives us 180.5 ohms. That is the resistance. I hope this has been also a very simple question for us to attempt. Don't always forget the units as you're getting your final answer. That has been another simple question. It's all about playing around with formulae. Now, we can look at another question. The other question is question 3. The other question is question 3. It says the resistance of a 0.01 molar sodium chloride solution in a conductivity cell was found to be 210 ohms. The specific conductance, now this term here, we talk of specific conductance, they are meaning electrolytic conductivity, is 4.5 times 10 power negative 3 Siemens per centimeter. Determine the cell constant. That's our question. Determine the cell constant. What shall we do here? This is what we are yet to see. What are we given? We are given resistance R as 210 ohms. We are also given specific conductance, which is electrolytic conductivity, as 4.5 exponent negative 3 Siemens per centimeter. They're asking us to get the cell constant using this information. Is it enough to get the cell constant? Yes. Just make a way, just get a way of finding a relationship between these two. You are aware that kappa is 1 over R times the cell constant, which is L over A. Now they're asking us this one. So kappa is equal to 1 over R times the cell constant. So what is our cell constant? Cell constant is kappa times R, which is 4.5 times 10 power negative 3 times R, which is 210. That gives us 0.945 per centimeter. Quite easily done. So that's our very simple calculation for that question. I have another example that I may want us to do. I have another example that I want us to do. The question is, question 4. A conductivity cell has electrodes of cross-sectional area of cross-sectional area 4 centimeters squared and 2 centimeters apart. The cell is filled with pure water. Of conductivity 8 times 10 power negative 7 S per centimeter, and a potential difference PD of 10 volts. Calculate the current that would flow through the cell. That's what we have. Area 4 centimeters squared. L 2 centimeters. Conductivity 8 times 10 power negative 7 S per centimeter. Potential difference voltage 10 volts. They want us to get current. How do you get current? How do you get current from your physics? Which relationship exists between current and this voltage here? So you are aware that from V is equal to IR, you know that. This implies that I is V over R. We have the voltage, you don't have the resistance. That is the importance of this information. So it's to help us get the resistance. You also know that from kappa is equal to 1 over R times L over A, we can get the resistance. How do you get resistance from this? From this you get resistance by saying that KRA is equal to L by multiplying this side. Meaning that R is equal to L over KA. Which implies that R will be L, which is 2, over K, which is 8 times 10 power negative 7. A is 4. This will give us our answer as 625000 ohms. So water has such a very big resistance. Now you can get your current finally as that voltage over, no, it is the voltage, which is 10 over that resistance, 6250 ohms. And your current will be 1.6 times 10 to the negative 5 amperes. So it's all about playing around with the formula you have and get your final answers that we are always interested in. We have 4 more examples to go. Those are examples are the ones we have. Let me do this one now. This is example 5. It says, calculate the mass of ethanoic acid that must be dissolved in a liter of water to make a solution of conductivity 75.08 per ohm centimeter squared per mole. If you see these units having per mole in them, I'm emphasizing this. If you see per mole in the units of conductivity, then just know that that is molar conductivity, even if the word molar is not there. Because we defined it as, we indicated it as conductivity of a solution of 1 mole of an electrolyte. If it's not molar conductivity, then the per mole is not always there in the units. I hope you note that. So a solution of molar conductivity that, or of conductivity that per mole, and electrolytic conductivity. .027 per ohm per centimeter. This is a bit different from the questions we have been doing. What are we given? We are given lambda C 75.08 per ohm centimeter squared per mole. We are given the kappa electrolytic conductivity at 0.027 per ohm per centimeter. But wagazachi kufuna mass ya ethanoic acid that must be dissolved in water. We cannot get that mass unless we have a concentration. So which formula are we going to use? We shall say lambda C, remember this formula, is, I told you here we use 2 formulae. It can be 1000 K over C over, or K over 1000 C. And I told you whenever we use each of these, this one is used when we have meters. The units here have an expression of meters in them. This one is used when we have centimeters in the units. So we shall use now 1000 K over C. we get the concentration now. Concentration will be equal to 1,000 K over lambda C when you make it the subject. And your concentration will be 1,000 times 0.027 over lambda C, which is 75.08. This will give you answer as 0.3596 molar or moles per liter. And that's the concentration should be now converted to mass by getting molar mass of ethanoic acid. Molar mass of ethanoic acid is 24 for the 2 carbons plus 32 for the 2 oxygens plus 4 for the hydrogens. That gives us 60 grams. So mass of ethanoic acid will now be 60 times 0.3596, which gives us 21.576 grams. That has also been a good question for one to practice. I hope you can now be able to do any question you come across, so long as you know what to do. If you know what to do, you can do any question. I'm doing my last example on this. And that is example 6. It says, the molar conductivity of a 0.1 molar ethanoic acid solution is 4.6 thiamine centimeters squared per mole. Calculate the Roman 1 electrolytic conductivity. Roman 2 resistivity. So we are given the molar conductivity as 4.6 thiamine centimeters squared per mole. And they want us to get the electrolytic conductivity kappa. We know the relationship between the two. Lambda C is 1,000 K kappa over C. So we want the kappa now. We want the kappa. So what do? We make it the subject. So what will be our kappa in this case? Kappa will be lambda C times concentration over 1,000, which is 4.6. I hope you know why I'm using 1,000, because this is centimeters squared. If it was meters, then the 1,000 should be in the denominator. So that's 4.6 times the concentration, which is 0.1, it's given here, over 1,000. What is your value of kappa for this? Your value of kappa is 4.6 times 10 power negative 4. What are the units, by the way? The 4.6 is S centimeters squared per mole. Concentration here is moles. By multiplying by 1,000, we convert that moles to moles per centimeters cubed. That's the purpose of that 1,000. So the 1,000 is not needed, it has no units here. If we are to convert to get the units. Now, what will be our units? What will be our units in this case? This will be S per centimeter. That will be the unit. S per centimeter. This is per mole because of the 1,000 there. So you finally get that as your kappa, as Roman 1. Roman 2 wants us to get resistivity. How do you get resistivity in this case? In this case, you can only get resistivity by relating it with kappa, because here we have nothing like cell constant, those things. So you know from kappa being reciprocal of resistivity, that implies that resistivity will be now the reciprocal of kappa. It will be 1 over 4.6 times 10 power negative 4. It will give us the answer as 2173.91 per Siamen, and then centimeter. Per Siamen is the same as now ohm, because 1 Siamen is 1 per ohm. That means 1 per Siamen is 1 ohm now. So you can give it as per Siamen centimeter or ohm centimeter as the unit of resistivity. So briefly, that's how we could go by this question. Does the time allow me to do one more example? I hope we have done enough of them. So practice, go to our book, Demystifying Physical Chemistry, page 702 and 703. You have about 8 questions to attempt. In case you get challenges, ask. In our next lesson, we shall be seeing factors affecting electrolytic conductivity. Then we shall also look at factors affecting molar conductivity. And then we shall explain them in detail. We shall later see variation of conductivity, molar conductivity with concentration or dilution. And then you have to plot some graphs and see how interesting those graphs look like. That will be our point of discussion in the next lesson. Thank you for attending. Have a nice time. God bless you.